So today's topic is really applicable to the real world because you see scaling in a lot of jobs. You see scaling in architecture, you see scaling in everyday algebra work, you see scaling in creating a table, you see scaling in a lot of different ways. And today we're going to look at scaling an axis, or scaling axes. I'm going to read you the paragraph, and as I read, I want you to underline important words as I underline important words. Okay, so the numbers on each axis of a graph or a number line show the scaling of an axis. The difference between consecutive markings tell the size of an interval. When you scale each axis, you must use equal intervals to represent the data accurately. For example, an interval of 5 creates a scale numbered -15 to 10 to -5 to 0 to +5 to 10 to 15. Ultimately, unequal intervals distort the relationship in the data. Okay, so I highlighted some important words. Axis. Okay, axis. When we look at our straight line here, this is an axis. Okay, and axes means more than one. Okay, scaling. Now, scaling here, you'll notice we have different notches on our graph. Now, but between each of these notches, these spaces have to be the exact same to represent the data appropriately. Okay, and these pieces here are called intervals. Okay, and those intervals have to be equal. So if we're looking at this specific diagram here, how large are our intervals if we know that this tick mark here represents 80? Go ahead and try to see if you can figure out what each of these tick marks represents if this tick mark represents 80. So there's a couple ways to do this. Some of you might have jumped straight to division or multiplication, saying, okay, well, I know I have 1 interval, 2 intervals, 3 intervals, 4 intervals. Now, if each interval is separate, but I know that they add up to 80, I can say, okay, I'm going to just do 80 divided by 4 and get that each interval is 20. That's a perfect strategy to use, and that would be correct. However, some of you may not have seen that right away, and that's fine too. So you might have just started guessing and testing. Okay, well, let's start with this being 5. And then let's add 10 to each one. So in here we have 15. Here we have 25. Oh, that doesn't quite work. So again, we're using guess and test, which is fine as well. Okay, so obviously that was too low, so we're going to move up. I'm going to say this is 10, and I'm going to go up by 10 each time. 20, 30, still not quite there. So you can guess and test all the way until you'd end up getting 20, 40, 60. Each of these spaces represent a value of 20. Therefore, they are the same, and the data would be represented scaled, meaning that each interval or each space in between each tick mark is scaled. Okay? This is all we're doing when we are working on projects in class, like your design project, for example. You're scaling your graph paper to represent a specific number of feet in the classroom. So, for example, if you have a wall in your classroom that, say, looks something like this, and then you have your scratch paper that's made into a bunch of grids that are smaller than your wall, but you want this entire wall to be represented in one of these little grids here, you have to scale your axis. You have to figure out how long this is. So say this was 15 feet. You would say that for every one of these boxes here would represent 15 feet. Therefore, 2 boxes would be 30, or 30 feet of your wall. It's just another way to look at perspective in mathematics, but also just in the real world. If you understand scaling, be sure to like this video, and remember, you got that math swag. See you next time.